Welcome to this second Further Maths video on solving differential equations. This one is on second order differential equations, second order homogeneous differential equations. Homogeneous means that we've got equals 0 on the right hand side here, and this is a linear second order differential equation, and it's of this form. Now, before we go on and solve these, we're just going to go back and consider what a linear first order differential equation would look like. So that is of this form: a dy by dx plus by equals 0. So that's first order linear differential equation. I guess you'd call that homogeneous as well, because it's got equals 0 here. I'm sorry about the shadowing on the paper. I think it should be okay. Now, this differential equation is in the form, or close to the form, where we can solve it using an integrating factor. In fact, we know that we don't need to do that. We can solve this very simply by rearranging. But what I want to do is I want to show you how an integrating factor would work with this, because we're going to do something very similar or we're going to extend the idea to the second order equations. So I'm just going to divide through by a, and we're going to get dy by dx plus b over a y is equal to 0. And then if we're using an integrating factor with this, our integrating factor will be e to the integral of b over a dx. Well, when we integrate constant b over a, then we're going to get e to the integrate b over a, we're going to get b over ax, and then we're going to take that integrating factor and we're going to multiply through, so we get e to the b over ax dy by dx plus b over a y e to the b over ax equals 0. We can integrate this and we get y e to the b over ax equals, integrate 0, we just get a constant, so is equal to constant of integration, which I'm going to call a. So y is equal to a e to the minus b over ax. So perhaps not surprisingly, we get an exponential function. And what I want you to notice is that minus b over a is the solution to the linear equation am plus b equals 0. Let's call it m equals that, is the solution to this equation. Now, what we're going to do is very similar for second order equations, but instead of having a linear equation like this, we're going to have a quadratic equation. So similar for second order. So if we've got a d2 y by dx squared plus b dy by dx plus cy equals 0, then we're going to use the quadratic equation am squared plus bm plus c equals 0. We're going to solve that equation. That equation, this is called the auxiliary equation. So we're going to solve that auxiliary equation, and then we're going to get general solutions which look something like this one did for the linear equation. It's a little bit more complicated because, of course, we know that a quadratic has either two distinct real roots, or it has one repeated real root, or it has two complex roots which are a conjugate pair. So let's just have a quick look at how we use the roots in those different scenarios. So there's our auxiliary equation there. We're going to say it's roots alpha and beta of the auxiliary equation am squared plus bm plus c equals 0. If the equation has two distinct roots, then we use them like this. We have a constant a times e to the alpha x plus a constant b times e to the beta x, where alpha and beta are the two roots. I think I'm just going to try and get rid of that shadowing by turning the light off. Right, I'm hoping that's a bit clearer for anyone watching this video. So that's if the auxiliary equation has a discriminant which is positive, b squared minus 4ac is greater than 0. If b squared is equal to 4ac, b squared minus 4ac is equal to 0, we've got a single root, alpha, and we get a general solution that looks like this: y equals a plus bx times e to the alpha x. If it's got two complex roots, so if b squared minus 4ac is less than 0, then we have to use them like this. If our roots are in the form p plus qi and p minus qi, then our general solution is in this form: e to the px times a cos qx plus b sine qx. So let's see how that works with the examples that we've got here in the course workbook. So let's start off with first one, example A. We've got d to y by dx squared plus dy by dx minus 6y equals 0. We're going to write out our auxiliary equation. AE is m squared plus m minus 6 is equal to 0. We're going to solve that. We can factorize this one. So that's m plus 3 times m minus 2 is equal to 0. So m is equal to minus 3 or 2. So our general solution is going to be y is equal to a e to the minus 3x plus b e to the 2x. Okay, part B then. And the other thing I should say is that I'm not going to go back and check that on this video, but I strongly suggest that you differentiate this twice and then check that your second derivative plus your first derivative minus 6 times your function does in fact equal 0. What you will find is the coefficients of the e to the minus 3x and the e to the 2x, which you're going to get from in both the derivative and the second derivative. When you add all these up like this, they're going to cancel out and give you 0. So part B, we've got d2y by dx squared minus 8 dy by dx plus 16y equals 0. So our auxiliary equation is going to be m squared minus 8m plus 16 equals 0. That's m minus 4 squared equals 0. So m is equal to 4, which is a repeated root. And that means our general solution is in this form. Y is equal to a plus bx e to the 4x. Oops, let's put that so you can see that there. Again, I would strongly suggest that you differentiate this twice and see that when you take d2y by dx minus 8 dy by dx plus 16y, everything cancels out, you get 0. For C, we've got the equation d2y by dx squared minus 4 dy by dx plus 13y equals 0, giving us the auxiliary equation m squared minus 4m plus 13 equals 0. If we complete the square on that, we get m minus 2 all squared is equal to minus 9. So m is equal to 2 plus or minus 3i. So we've got a complex conjugate pair of roots there. So our general solution is going to look like this. Y is equal to e to the 2x, so that 2 comes from here, times in brackets constant a times cos of 3x plus b sine 3x. Again, I suggest, and it's a little bit more complicated this time, finding the first and second derivatives, but just verify for yourself that it does satisfy that differential equation. Right, we're going to go on now to look at an example where we can solve the differential equation and then use boundary conditions to get a particular solution. And you can see that where we've got a second order differential equation, we need not only values of x and y, but we need something else as well. In this case, we've got a value of the derivative. Another possibility that we might have had would be x equals 0, y equals 0, and then another pair of x and y. That would also work. So let's go ahead and solve this differential equation. So we're going to write the auxiliary equation, m squared minus 6m plus 9 equals 0. That's m minus 3 squared equals 0. So m equals 3, and it's a repeated root. So the pattern for our general solution is y equals ax plus b e to the 3x. We're now going to use these values. So we're going to say at x equals 0, y equals 5. So 5 is equal to, if we substitute 0 in here, that term is going to be 0. So we just get b from the bracket. So that's b e to the 0. So b is equal to 5. To use the second value, the dy by dx equals 0, we need to differentiate this. So we're going to say dy by dx is equal to, differentiate that bracket, that's going to be a times e to the 3x plus ax plus b times, differentiate the e to the 3x is 3e to the 3x. At x equals 0, dy by dx is equal to 3. So 3 is equal to, well, if we put 0 in there, we're going to get a e to the 0. If we put 0 in there, we're going to get b times 3e to the 0, so plus 3b. We already know what b is, so we've got 3 is equal to a plus 15. So a is equal to minus 12. So that means that our particular solution is y is equal to 5 minus 12x e to the 3x. So we've now seen how to solve second order homogeneous differential equations, that is those ones with equals 0 on the right hand side. You should go away and practice that. That's in exercise 7b in our textbook. And then we'll be back to have a look at what we do when we have non-homogeneous second order differential equations. So that might be something like this equation here, but then with maybe sine x or e to the 3x or e to the x on the right hand side of the equation. Thanks for listening.